Okay, I think I am streaming. Hello, it's been a while. I probably should have planned this a little better now that I think about it. Now that I am live on YouTube, uh, probably should have thought about what I was gonna do, or at least how I was gonna start. Um, Hello. I don't know if anyone is there. Or if anyone is watching. I don't know if this is going to be saved afterwards. I kind of thought, well, what I need to do is next semester, this coming semester, I'm teaching some classes on Max MSP again at the University of Leeds. Shout out University of Leeds. And one of the things that I want to do in that class and also in a composition class that I'm going to be teaching is think a little bit more about the frequency domain, pfft stuff, and how we can do interesting kind of signal processing stuff. And I've taught a class on this before that was kind of very top level, kind of just like a little taster of frequency domain stuff, but I kind of thought, you know what, like it's been years since I wrote that, and I'm kind of trying to refresh all my teaching, and I don't do that much Max MSP anymore. I don't get to play around with it so much, so I kind of thought as a good excuse to kind of rewrite the classes on that, that I would spend a little bit of time kind of playing around with frequency domain stuff and kind of relearn it, because it's been years since I've built any of my kind of phase vocoder, pitch shifters, all that frequency domain good stuff. It's been years since I built those, and I kind of just reuse those patches. So I thought, right, I'm going to start from scratch. I'm going to go back. I'm going to read the pfft docs. And I thought, I know, that'll be riveting viewing. So I do mean to record like a proper video at some point, and I actually wrote the script for the kind of first part, the introduction, the kind of history of phase vocoding, like a year or two ago, and never recorded it because I didn't really have the follow-up, which was the sort of practical stuff, the bit that people want to do. So maybe this will be a good kind of learning environment for me to do that. So basically, yeah, I'm going to look at phase vocoding in Max and frequency domain stuff, and I'm going to start. I'm realizing now this is like the first time I've logged into Max, aside from teaching, probably in a year since I did those Max 9 videos. So this is obviously going to go terribly. Oh, Oliver, I'm discovering that this was maybe not a great idea to do this live. But let's see. Okay, so let's start with pfft. So I should probably like read the docs for this, but from what I kind of remember, in Max we're dealing with the kind of pfft object as being like that kind of wrapper, right? So all of the kind of fiddly Fourier stuff is happening within here. And it gives us some basic operations that kind of takes care of that. But we have to deal with sub-patches and things like buffer size and windows, if I remember. Okay, so I don't know if anyone is there to even hear this, so I'm just kind of talking to myself. I guess it'll be good. I've got a kind of rubber duck situation going on. Right, so let's start at the start. Let's start with the pfft docs. Pft. Oh, you gotta be kidding. Have I forgotten the shortcut for reference docs? Apparently so. Okay, Maybe this will maybe I'll find my niche in kind of bedtime stories for computer music nerds, and it'll just be me reading the documentation about spectral processing. Shall I I'll just whisper it. Okay, the pfft object is designed to simplify spectral audio processing using fast Fourier transform, FFT. In addition to performing the FFT and the inverse fast Fourier transform. So let's assume I'm gonna talk at the camera as though you are a student who has never encountered this before. FFT, fast Fourier transform, is our way of deconvolving, I guess. That's not the right word. Kind of decomposing a signal into a set of data that we can manipulate in some way, right? So we take an audio signal in, so that's what's going to pass into our pfft object. We're going to have an audio signal that comes in. You know, that's like every normal kind of time domain is what we would call it, audio signal, and that works kind of through basic digital audio theory. So we have our waveform that moves like this over time, right? And then the kind of frequency controls the pitch and the timbre and the things that we hear, right? That's not what's happening in the frequency domain, right? So we're going to perform this operation, this fast Fourier transform, and it's going to convert that audio signal into kind of two streams of kind of complex numbers. So we'll have real and imaginary numbers, and kind of functionally speaking, from what I remember, that is the polar and Cartesian numbers. Oh shit! I need to look that up in a minute. Okay, let's get a notebook. What do I need to? What does Oliver not remember? Right. Real and imaginary. Let's look that up in a second. Okay. Right. So that's what we're going to do at the point of fast Fourier transform. And then the inverse fast Fourier transform is at the kind of end of our signal spectral processing. We're going to flip it back. So we're going to convert those real and imaginary numbers back into an audio signal, right, that we can then listen to and deal with. Okay. That was a massive tangent for the second sentence of the documentation. So this bodes well. pfft, with the help of its companion FFT in and FFT out objects, so they're the things that go inside the pfft object, manages the necessary signal windowing, overlapping, and adding needed to create real-time, short-term fast Fourier transform, short-term Fourier transform analysis and resynthesis. Okay. Oh, that's nice. So Max is doing all the difficult stuff for us. That's kind of what we want. Discussion. The number of inlets on the pfft object is determined by the number of FFT in and or in objects. Oh, okay. Yeah, there's like separate FFT in, which is our audio in signal, and then there's just regular in inlets that will take in other values. Patches loaded into a pfft object can only be given signal inlets by FFT in objects within the patch. See FFT in for details. Okay. Well, maybe we'll do. Now, do I want to like actually read a kind of reference at this point, or do I want to just wing it and see what I remember? How much muscle memory have I got here? Okay. So, what are my arguments that I want? Right, subpatch name. What should we call this? Let's call it spectral. And then I need FFT size. Let's go 1024. overlap factor. So my overlap factor is my windowing, I seem to remember. Basically, how much overlapping is happening between those kind of bins. We'll talk about bins again in a second. What's my default? Hop size, that's the term. It's basically the offset, right? The amount that if you have a wave here, and then you have another one like starting halfway, or maybe a third, or maybe a quarter, and how many. Usually if the frame size is set to 512 and the overlap is set to 4. Yeah, so, okay, so let's just say 4 for the time being. Start onset. Okay, I think they're optional, so I'm going to leave those. And let's take an audio signal so that we know kind of what we're doing here. What's the amen break, Jungly? Oh. Max, what are you doing to me? Okay, I'm gonna click this. It might start playing, so if anyone is there, just check your headphones a second. I don't want to blow your ears off. That was a little loud. Let me turn that down. Can I turn that down? What's OBS doing? OBS. Let's bring that down a bit. Okay. Someone shout if it's too quiet or too loud. I'm not entirely sure why Max is stopping me from doing this. Is it SF player? No, it's playlist, isn't it? Can I at least just drag the audio in? Don't make me go diving into my file system to look for it. Oh my god. You are making no friends here, Max. Okay. So we don't need, oh god. Right, that's playing. We have audio. We know we have audio. I can monitor it here. So we have audio coming into our pfft. Now, nothing's happening at the moment. So let's open that. He said, let's open that. Control, double click. What are you doing to me? What the hell? I've never encountered this. So holding control Double clicking is not opening my patch. Now I have a stupid keyboard, so I appreciate that something might be going wrong here, but also nothing should be going wrong here. What's happening? Is it genuinely just not creating a sub patch for me? That's ridiculous if that's the case. Are you going to make me do this? Are you going to make me save? Okay. Right, let's okay, so this is going to be spectral main, and we'll have to create a new patch. Oh, that's big. That's going to represent my sub patch. I feel like that can't be right, but what's it called? FFT in? FFT in. I think maybe they have to be numbered. Okay, so let's save this now, and this is going to be spectral. You used to have to do this weird thing where you used to have to like name it pfft. I don't know if we do that anymore. Let's just call it spectral. Maybe I'll call it spectral FFT. No, I have to call it spectral because it has to be the name of the thing. Does it need the max pat? Let's try that. Let's see if it does. Okay. Is that linked? Oh my god. It has been far too long since I've done much max. And this is what I'm doing to pay for it. Okay, so far I have managed to create a pfft object, and that's it. And it's taken me the better part of 20 minutes. Okay, right, so what do we have here? Real input. That should be imaginary, I guess. Imaginary input, and then what's this? FFT bin index. Ah, cool. Right. So let's talk about bins. So if we were doing an analysis of our audio signal coming in, so in this case we've got jongly coming in, right? Where we've got our AMN break coming in, and we are doing some FFT conversion, transform, and we're converting that signal into real and imaginary numbers, right? And these are going to be in tiny slices. So rather than a kind of continuous signal, we're dealing with these kind of slices of time, right? Maybe that's a window, which equates to our sample size that we specified. So in this case, spectral.maxpat, 1024 samples. I can't think what that is. If I'm at sampling rate of 44,100, it's tiny. It's like 20 milliseconds or something. It's less than that. So we're slicing up our signal into these little slices of 1024 samples, right? And each time we do that, we're also, so if we slice it horizontally into 1024 samples of time, we're also doing it vertically, right? We're slicing it up into 1024 bins, right? Which is slices of frequency. So, you know, a low frequency moving up to a higher frequency. I think the range of that again, related to that kind of frequency slice size 1024. So we're basically taking our double our sampling rate, I think double, something to do with the Nyquist theory coming in there, and slicing that up into 1024 bands of frequencies, right? Maybe that's a better way of thinking of it than bins. If we kind of call it bands, we can think in terms of bandwidth. So you can see that the size of our FFT kind of affects the fidelity to an extent, right? The larger the number, the bigger the chunk of time, but also the more bands or bins that we slice our frequency up into, right? And for each of those bins, I'll try and say bins now, for each of those bins, we're kind of going to do an analysis, right? So we will basically say, okay, at the first bin, which will be like 0 to something, 50 hertz, what's the amplitude level like here? Is there signal? Like, is there something going on here? And then it'll record that number kind of, you know, on a 0 to 1 scale or something like that. And then it'll move to the next bin. Okay, 50 to 100 hertz. Is there much happening here? What's the amplitude level? And it's moving all the way up to our sampling rate. So what we get then is this index of bins and kind of frequency information, amplitude information about that frequency, right? So we're effectively, what I remember, we're effectively kind of analyzing our signal in tiny chunks of time and in tiny chunks of frequency, right? So that's kind of what we're doing here when we get our real number, imaginary number, and bin index. Now, what I can't remember is how that real and imaginary number equates to frequency and amplitude. So I need to look that up in a sec. Because that's what's going to happen at the point of the inverse Fourier transform. So where we take those real and imaginary numbers of that analysis and we convert that back into a signal, right? I can't remember how that happens, so I want to look that up in a second. Okay, so what we should be able to do then is, let's just go, what's this one? Real output, imaginary output. Okay, so it's discarding the bin index. We don't need that. I wonder what that's doing. Okay. So if I've done that right, and that's a big if, we should now have a signal coming out here. Okay, that bodes well. So what we've done then is we've taken this signal, we've done this Fourier transform, converted it into a signal that is, you know, not an audio signal. We can't listen to this, right? I mean, you wouldn't want to listen to this. Can you listen to this? Can we even do that in Max? I don't know what you'd hear. Probably wouldn't hear. What's a good way of seeing what's going on here, aside from that? I mean, you can see that signal scope doesn't look like... Well, it actually doesn't look that dissimilar. Okay, that's not helpful. What happens if we try and... Going to be playing fast and loose with everyone's hearing if this works. What could we do? Well, let's put a live gain up first just to see what. Oh, that's my old session notes. That's helpful. Ooh. Is this a terrible idea? I think it probably is, but I still want to try it. It's interesting, actually. Okay, it sounds like trash, obviously. But it's interesting that because we've taken a percussive sample, right, we've taken that amen break, that you can still distinguish what that is. Right? That's kind of interesting. I wonder if this happens. I wonder if this is. So that is. What is that? Is that imaginary? So what happens if we do it? Oh, this keyboard. No, I'm gonna. The left and right really bugs me. Like if things are, I can't. My brain doesn't do it if they switch. Okay, so we're gonna have real signal on the left side. We're gonna have imaginary signal on the right side now. Previously we had it the other way. Okay, so that's, you know, we've kind of got. I'm not saying you would want to listen to that by any means, but that's what happens if we listen to the real and the imaginary signal. But there must be something happening there. Because I don't know. I would love to. I would love to see what those numbers are, right? Because I kind of think of this. I think of this analysis, this bin analysis, as being like a big spreadsheet, right? Where we have cells going up for each bin, right? For each frequency bandwidth, and then we have like an amplitude kind of number. That maybe that's just a bad way of thinking about it. I'm not sure. Let's see what they have to say in the reference. Very little. Max has crashed. Max. Right, hold on. I'll reload. This gives me a good excuse to eat some gluten-free biscotti while I wait for it to load and drink some tea. But I'll be back in 30 seconds. I'm keenly aware that no one wants to hear me chewing gluten-free biscotti, so okay. I love that Max crashed while trying to open the help documents. Like, I wasn't even doing anything difficult. I wasn't even doing anything weird. Like, with Max, it just crashed trying to open the reference. This program is a hot mess. Right. We've successfully opened the reference. Thank you, Max. Okay. The FFT in object provides a signal input to a patcher loaded by the pfft object. Okay. Not sure that I was expecting. Okay, so this will tell us a little bit about maybe what we were hearing there. This output contains the real values resulting from the fast Fourier transform performed on the corresponding inlet of the pfft. So that's our kind of main patch, the outer patch, right? The output frame is only half the size of the parent pfft object's FFT size, because the spectrum of the real input signal is symmetrical and therefore half of it is redundant. Okay. The real and imaginary pairs for one spectrum are called the spectral frame. Frame, that's the term. Okay. So the frame size in our version is 1024 samples. Okay. And the frame size is therefore equivalent to the number of bins, I guess. Okay. So that was the... Is that the real or the imaginary? Which was that? That's the real values. So the middle output, same again. Output contains the imaginary values. Output is only half the size. Symmetrical, redundant. Okay, cool. And then the outlet, the outright outlet, a stream of samples corresponding to the index of the current bin whose data is being sent out in the first two outlets. This is a number from 0 to frame size -1. Okay. Okay. So there's something going on there, I kind of remember now, about the way that this is being fed out. Because we're doing this on a live signal, right? We're slicing it up into these 1024 sample slices, frames. And we're doing these kind of discrete operations, but we're hearing a kind of live signal. So that bin count, right? So it says current bin whose data is being sent out of the first two outlets. So it's counting out across those bins in series, right? Over the course of that 1024 samples. So it's doing this kind of, I mean, this is, too fast for us to hear, right? Let's say, oh God, I wish I'd done the actual maths on what that is, but let's say it's something like 20 milliseconds, right? It's certainly not 100 milliseconds because we'd kind of hear that. But like when we're dealing with kind of granular synthesis stuff, we're maybe dealing with like 50 milliseconds, right? So it's a very short amount of time, but what we're doing is we're kind of doing this like, I want to use the term bodge, but that's probably not the technical term, where we're taking this, continuous as much as our sampling rate allows. We're taking this continuous signal, slicing it up into these frames, and then kind of iterating out across that over the same length. So that's why our frame size, I think, is the same size as the bin count, right? Because we basically say, right, we've got this amount of time to iterate across this stack of bins. So you go 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 1024 over that amount of time. And I guess, I mean, obviously we're going to have aliasing issues, but I guess that's kind of why spectral processing sounds a little bit funky sometimes. It's kind of there's something not quite right about it, right? Because that's ultimately what we've got when we resynthesize, right? When we perform that inverse Fourier transform, we've kind of got this like simulacrum of the original signal, right? It's not the same because it's been decomposed and then resynthesized. So it's never going to be a perfect match, right? I think that's the case. I assume it's got to be a lossy process, right? There is something being lost in that translation. I don't think it's perfect. I don't want to go back to reading like Fourier theorem. I'm going to avoid that if I can. Okay. 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 What have we got here? So I think I'm trying to think of this from memory rather than just like opening up the examples. But the kind of classic example is where we cross synthesize two signals, right? Where I think that's like where we take the real signal from one signal and the imaginary signal from the other and cross them. But what would that be doing? Let's try it and see what it does, and then I'll open the example, and I bet there's a more helpful explanation there. Okay, so I am going to want another one of these, I think. And then am I convolving them, or am I just crossing them? So am I going to discard one? Let's take two. But then we're gonna cross the streams. So this is going to be the imaginary output of signal 1 is going to go to the imaginary output of signal 2. And then the real to the real and the imaginary to the imaginary. And I'm not doing anything with my bin count. Let's see what this does. Maybe it'll give us a better understanding of what's going on with, with those real and imaginary values. I say better understanding. A better understanding would be reading the Wikipedia page for Fourier theorem, I have no doubt. But I'd much rather fiddle about and have a guess. Apologies, any engineer or mathematician is just sort of did a shudder just then, I imagine. Oh wait, no, that's not going to work. I've just got one signal. Let's go with, what's the audio, isn't it? What's the one of someone counting? I have that somewhere. Maybe it's C sound. Would help if I was looking on. Doesn't help that I've got loads of like impulse response sounds here. What do I want? Okay, let's take E piano. See, that dragged in absolutely fine that time. So maybe we should do one at a time. So this is going to be, I'm going to have the Amen break playing. I'm going to have this electric piano note playing. They're both pretty identifiable there. It's not that interesting, is it? And this would be flicking it the other way. Nah, not into that. So that's not what's happening. What happens if we just add the signals together? Am I doing this in stereo for some reason? That's effectively what I'm doing now, isn't it? So I'm maintaining kind of real to real, imaginary to imaginary, but I'm adding the two together. Okay, well that's relatively high fidelity and won't turn off. What? Ugh. Okay, so that's not doing anything interesting. Okay, so let's make this the product then. Once again, okay, it's not what we would call pleasant, but it's interesting, I think. Let's just maybe revisit what our sources are. Let's go with the kind of, let's go with something with a kind of higher noise source. Let's go with the rain stick. Where's that? Gives it interesting. Okay, at this point I'm just guessing, so I'm just going to stop that. Right, let's have a look at the Max examples and see what they say. If I can remember where the Max examples are. There we go. pfft fun. Cross dog, that's what it's called. Jeez. Okay. Okay. This cross-synthesis implementation uses an older MSP technique based on overlapping FFT and IFFT pairs. Oh, so this isn't the cross-synthesis one. Okay, let's come back to that because I want to try and remind myself what that does. Maybe it was that. Okay, let's see what the convolution workshop is. So is this closer to what? Oh, then we can. It's funny that we lose so much. So there's like a, you know, there's lower frequencies here, right? I'm not going to go out and say there's loads of bass here, but there's like a decent amount of kind of lower frequencies here. But they're not here. But kind of once we hit that midpoint, we kind of lose them all. So I think it must be taking the frequencies that are present in one and the frequencies that are present in the other. So in the sense, yeah, it's a bit like kind of what you would have in like a convolution reverb to an extent. So we hear the frequencies that are present in both. So we would have more bass, I guess, if this was a... Is there going to be more bass in this cello? It sounds like the worst Carplus strong synth. Twang. But it's, I wonder what causes that warble. I mean, so let's kind of see how the sausage is made. Let's, what's this? Okay, so that's just okay, that's just mixing. So let's just hack this a little bit and see what's kind of going on. I want to hear what it sounds like without that delay. And then what if I bring the delays in? Well, that's my original signal. Oh man, if we slowed this down, we'd have some banging post-rock at this point. Godspeed, eat your heart out. All right. Anyway, okay. So, I wonder what that. The delay objects compensate for the 2-frame delay inherent. Oh, I didn't realize there was a 2-frame delay inherent in real time. So is that the time it takes to iterate out across the bins? Must be. Because they said that that was halved because of redundancy, so maybe it does the full thing. Interesting. Okay, so anyway, let's see what is going on in here. Okay, so we're taking the real and imaginary of our second inlet. So in this case, that is the drums. And car to pole. So we're converting a Cartesian to a polar coordinate, I think. Oh yeah, signal Cartesian to polar coordinate conversion. But what is that for? What's that doing? God. This stuff is all frustratingly like, oh, I remember reading about this 20 years ago, 15 years ago, and I remember almost nothing about it. So we take our Cartesian coordinates, which are xy coordinates, and we convert them to a polar coordinate system. So that is, oh, amplitude phase. So okay. And what does that equate to? Is that degrees? Like phase being my kind of degrees, I guess, and amplitude being that. So okay, so for each frequency bin, we're determining the phase and the amplitude of that bin, right? So why in the cross synthesis example are we doing this Cartesian to polar? Because is that not what's done? Is that not what the real and imaginary numbers are? Is that not what's done in? Like, so I see that they're using it to clip the amplitude. Basically just keeping it between 0 and 9, but I don't, could you not, is the real, does the real input not go from 0 to 1, or? I mean, what do I get if I, okay, let's rebuild this. Let's rebuild this. You can have that back. Let's get rid of this. Let's get rid of that. So they had effectively this, and then they had car to pole. And then they were clipping it. From 0 to 0.9, I think. Like that. And then they were only doing it with the real, but in this case, the amplitude value. And that was going over here. Okay, so let's see what that is happening. Let's just check that. Okay, it's doing something, but I've got myself distracted by hating this. I'm gonna do oh. Because I just want something that's continuous. And apparently just intonation. uh hmm. Thought. Hmm. If we just got none of those frequencies present in the rain stick, are they all higher frequencies? No, that can't be right. Yeah, I mean, let's have a bigger spread. We've definitely got a signal going in. But it should just be a continuous static signal. I wonder why it's not doing that. Feel free to chime in if anyone spots what is undoubtedly going to be a really annoying small problem that we'll go, obviously, when we figure it out. Not that. I mean, there's something there, but why is it so quiet? Let's do a little frequency sweep. God, that sounds awful. Give me some drums. That's really strange that it's 4 sine waves, but it's, I mean, that sounds. I mean, just as a, I want to see what. Okay, so I want to understand a little bit more about what this Cartesian to polar transformation is doing, and so I'm going to do that in 2 ways. The first way, I'm going to do it out in the main patch, and I'm going to swap our drums and our sine waves. So at the moment, the sine waves are having that Cartesian to polar conversion, and now I'm going to swap it. So the drums will have that Cartesian to polar coordinates conversion. Okay, now this makes sense. This makes sense. This makes a lot of sense. So I think what's happening here is we've got our kind of harmonic content, right? This is our main frequency content of our signal, whereas the one that's getting the Cartesian to polar conversion is mainly forming our amplitude content. Okay, that's cool. So we maintain that sine wave, but we get the rhythm of the drums coming through a lot more. That's kind of cool. Can I change the speed? Can I change the signal of this? I can't, can I? I would love to slow this down and let me see if it'll let me do that. Is that is signal gonna? This isn't a groove, so no. I wonder if I've got a snippet for this. Hey, there we go. Let's do... Wait, no, SF play, that's not what I want. Oh, come on, that's not mine. That's the most useless snippet. Cycling 74, what are you doing? No one needs that. Where are my snippets? Where the hell have mine gone? Oh. Honestly. Does that work? I should probably specify stereo. I don't know if that start loop is not a valid attribute. Fair enough. You got me. You got me, Max. But they were back in the Max reference. They were talking about that delay, right? So it was delayed by. Was it that? No, it was double that, wasn't it? I mean, oh, is that in milliseconds or is that in samples? Because 2000 samples is not the same as 2000 milliseconds. I'm going to assume that it's samples, because otherwise that would be ridiculous. Okay. I kind of like that. That's interesting. So that's what that's doing. And then the clip amount is just keeping that contained. So if we... What happens if we start to play around with this then? Oh, no. Unpleasant. Excuse me. We've got some very bizarre vibrato going on here. I don't hate it. But it's not super interesting in terms of that's giving us that nice static. Does it make a difference if I swap the real and imaginary values here? Probably. Not to a huge extent though. And then if I just bypass this completely, so if I go back to what we were doing originally, what I was doing originally, oh yeah, no, that's why it sounds awful. Now, in terms of the frequency content, that sounds awful, but actually, apologies, folks. But we still have that kind of amplitude fingerprint going on there, so that's kind of interesting. Let's put it back there. But the frequency content then of the drums is not making too much difference. Guess we could test that. We could put the rain stick back in. What's fem voice? Yeah, so there's almost no difference in the frequency content. So if she's saying shh, which is just all kind of noise, versus like the vowel sounds, which have very clear like frequency kind of center point. There's no difference there in what we're hearing in terms of the sine wave. We're just getting those same blocks. And even when it's slowed right down so the frequency is really low, we're not hearing a difference. Voice in the left, sine waves in the right. Anyone joining the stream right now is not going to have any idea what's going on. Apologies. So we've got noise coming back in there. The shh. I mean, I could just listen to slowed down voices all day. Let's see what else. What else can we learn? So let's go. Let's take this, right? Because I think the Rhodes piano, we could probably tune our sine waves to not be a million miles off. And then I wonder if we swap them back over what we can get now. I'm not going to spend ages tuning that. Okay, that's unpleasant though. Let's not do that. Oh, this is too... Okay, no. Right, let's get rid of... Oh. We're really not getting very much amplitude differentiation. Okay, I'm going to swap them back over now. No, that won't make any sense, will it? If we've got the... Have I labeled that wrong? No, it's right. It just had the cables. Oh, it's that left-right thing again. I hate it. Okay, so now we've got the frequency content of the Rhodes piano and the amplitude content of the sine wave, which is just static. So that's not going to do That's not really going to do anything, is it? Because it's just a... Let's get rid of that. And let's go back to... Well, actually, it's just where we started, isn't it? If I dropped the amen break back in, we're just back. That's kind of cool. I quite like that, actually. I'd be into... Oh, there's all those new Ableton audio effects. I was going to build a delay quickly, but I bet there's a ready-made one now, isn't there? What are they called? I just want a delay. Oh, delay, obviously. What do I want? An echo? Well, let's put an echo on. What are my arguments? What? Getting flashbacks to the first stream I did here where it's all just... Oh, it's messages. Oh, okay, that's fair. I've gone massively off track here. So what can we do? Kind of play around with this. I'm curious if there's anything we can do here with the frequency bin index. I mean, I know there is in the sense of making like a spectral filter. And maybe I'll do this again later in the week. Maybe I'll do another one of these streams. But you can basically hook up a multi-slider object to give you effectively like a fader for each one of those bins. So we talked about bins earlier on being like a kind of frequency bandwidth, and we're doing however many of those depending on our frame size. So in this case, we've got 1024 bins, frequency slices of this signal. And you could hook each of those up to a slider and have 1024 frequency sliders, like just a ridiculous parametric EQ basically, so you could control those. So we could do that with that bin index, basically to figure out, there's what is it called? There is the Max object example called Forbidden Planet, right? It's after the film. Where's that? There we go. Oh god. So you can do that. So this is basically just hooking this multi-slider up to yeah, okay. So It's using peak and index. So we could do that, but I wonder if there's something that we could do to play around with this idea of doing this conversion. What do we get here? If I just want to understand a little bit better about what this is. This is a polar coordinate. Well, that's not helpful. Because I guess we can modulate it in some way, like an additional signal maybe, or wait, I wonder if we put the delay in here, right? So we took it out of here. Can we do that in a pfft object? What do we want? Let's just assume that that's working in milliseconds. Let's do a big delay. Ugh, really? This is, no, I don't understand. I'm fearful of these new technologies. Let's just do a tap in and a tap out. What? Because we could also make this like a multi-tap delay. But let's do like 400, fine. And 700. Oh no, hold on. That's a question. Because I'll be sending separate. No, that's not going to work. Well, it might work, but it'll sound shit. And be sending separate values, like mismatched values, to the real and imaginary, which we don't want to do. So actually, I'm going to have to sum these delays, which is fine. That should be smoother. The more I think about this, the less interesting this actually might end up being. It doesn't sound horrible, but maybe we could do a kind of pseudo stereo thing. Right, wait. where we just split these. How am I going to do this? 700. 700, you come over here. I wonder what would happen. Yeah, so the main of that is coming from. Okay. I'll have a think. I feel like there's something we could do here with this catapult object. But okay, that was a fun kind of hands-on playing around with trying to understand a little bit more about what this is doing. I really didn't get as far as I was hoping to get, because I was hoping to get more into kind of convolution, other kind of signals like reverb and even phase vocoding, which, you know, given that we basically made a cross synthesizer at this point, maybe I need a little bit more playing around time. So maybe I'll try and do another one of these over the next few days, just while I play around with this and try and find my bearings before I start planning my frequency domain classes again. But yeah, this was fun. If you happen to be watching this after the fact, I hope some of it made any sense. I'm not sure how long it will stay online for, but anyway, drop us a comment and say hello if you're there. And yeah, thanks so much for sticking with it. I will see you next time. Thanks, folks.